Look at this context-free grammar. We'll feed it the string a plus b times c. We can build a parse tree grouping the addition operation at the bottom. But using the exact same rules, we build a completely different tree, calculating b times c first. We have one string, but two mathematically distinct parse trees. In compiler design, this is a fatal flaw called ambiguity. Compilers cannot tolerate this. The issue stems from the grammar's flat structure. Both the addition and multiplication operators sit at the exact same hierarchical level. The rules never specify that one has a higher priority than the other. A parser does not know basic math. It has no external understanding of standard order of operations. It only understands the geometry we give it. To fix this, we have to engineer a solution directly into the syntax. We must physically alter the grammar to force a single, rigid geometric shape that inherently dictates the correct order of operations. Our first task is establishing precedence. We solve this by splitting our flat expression rule into a strict three-tiered hierarchy. This diagram shows our new architecture. Layer 1, expression, handles addition. Layer 2, term, handles multiplication. Layer 3, factor, handles atomic variables. Linking tiers generates rules. E produces E plus T. T produces T times F. F produces an identifier. This creates strict downward paths. Let's test this layered architecture with our problematic string, A plus B times C. To generate the plus sign, the root E expands into E plus T, trapping addition near the top. For multiplication, the parser moves down. The T node expands into T times F, pushing it physically deeper. Finally, variables plug into the lowest factor leaf nodes. A parser will always evaluate nodes strictly from the bottom up. The deepest leaves must collapse into results before the nodes above them can process. Because multiplication grows deeper into the tree, the parser must evaluate b times c first, passing that result up to the addition node. We have mathematically enforced precedence purely through topological depth. Multiplication always happens first, because the grammar buries it deeper than addition. Depth solves precedence between different operators, but an issue remains when operators share the exact same layer. Consider the string a plus b plus c. Both addition symbols sit at the expression level. The parser needs a rule to decide whether it should group the left side, a plus b, or the right side, b plus c, first. This specific tie-breaking logic is called associativity. Standard arithmetic dictates left associativity for addition. The evaluation must cascade continuously from left to right. In the expression rule, the recursive e is the first item on the right. Expanding this leftmost e repeatedly creates a heavy leftward tilt. This staircase pattern pushes the leftmost addition to the lowest point, guaranteeing it evaluates first. If we wanted right associativity, typically used for assignments like a equals b equals c, we would simply place the recursive non-terminal on the far right side of the rule. Vertical layering dictates precedence. Lateral placement of the recursive variable dictates associativity. There is one final requirement for a complete mathematical grammar. We need a mechanical way to force a lower precedence operator to evaluate first, using parentheses. If we input open parenthesis a plus b close parenthesis times c, addition must supersede multiplication, but our current geometry forces addition to the top. We add a final rule. A factor produces an expression in parentheses. Looking at the parse tree, multiplication forces the structure down, but the factor node generates parentheses enclosing a new e. This recursive wormhole loops the parser back to top-level rules, rendering addition deepest. Because this entire subexpression is now physically below the multiplication node, the addition is fully evaluated before the higher-level multiplication can trigger. Parentheses do not break the grammar's geometric logic. They utilize it, embedding a completely new root deep inside the leaf nodes to cleanly reset the hierarchy. This completed architecture is the expression-term-factor grammar. It structures complex inputs like A plus B times C plus D. Operations execute bottom-up, with leaf nodes collapsing into concrete values and bubbling up to the root until a single final result remains. We removed ambiguity without ever teaching the parser mathematics. We simply locked it into a rigid structural geometry. But this perfect architectural solution carries a hidden cost. Let's isolate the specific rule we use to enforce left associativity. E produces E plus T. When a standard top-down parser tries to apply this rule, it reads the E on the left and is immediately commanded to look for the first element on the right, which is another E. It does this before it reads a single actual character of input. That second E instantly commands the parser to find a third E. The third demands a fourth. This creates an inescapable cycle, a fatal infinite loop known as left recursion. A top-down parsing system will plunge into this tunnel and never return. Left recursion will violently crash any standard LL compiler. And herein lies the paradox. The exact lateral geometry we require to fix mathematical ambiguity is the very thing that destroys the parser. To build a working compiler, we now have to solve the solution.